Hello, folks. Welcome to Chapter 5, where we enter, I want to say the second half of calculus, but there's some tidbits at the end. This is kind of our next really big topic. So first we did limits, then it was derivatives, which are rates of change. We are moving into our next phase of calculus, which is areas under curves, and you're going to see the magic that can do for us in calculus. It's a different kind of magic than the derivatives, but dare I say even more amazing? I don't know. You can be the judge of that. All right, so what we have done so far, thinking about derivatives, is taken a curve and through calculus being able to find the exact slope at any point. No longer this average change in y over change in x, no longer this rise over run idea, but an infinitely small change in y, an infinitely small change in x, which gives us the exact slope of that curve at an exact point. In other words, the slope of a tangent versus the slope of a secant. So when we're working with something like a velocity function, if you take the slope of that and you think of it in terms of a rise over run, what you have is meters. Whoops, I didn't mean to do that. Okay, ruined my, what you have is meters per second over seconds, and you end up with meters per second squared, which we know is an acceleration. So in other words, when you have a velocity graph and you do the derivative, what you're finding is the rate at which velocity is changing. And we know that physically that means acceleration, a speeding up or a slowing down, or a changing of direction. Could be either or both. Okay. What we want to look at now is a completely different aspect. What we want to look at now in this second kind of big chunk of calculus is what happens when you have a function that is a rate of change. Instead of talking about how quickly it's changing, start talking about any cumulative effect that it may have over time. So for example, this is a velocity. If I said to you, I'm traveling at a velocity of 60 miles per hour for 2 hours. Sixth grade science would tell you, oh, well, 60 miles per hour, 2 hours, 60 times 2, it's 120 miles. Easy, right? What we encounter in calculus is a speed that's constantly changing, or a velocity that's constantly changing. And that's actually more realistic. So it's not going to be as easy anymore as saying, okay, here's how long I've been going and here's how fast I was going, so let's just multiply. But we're going to use that same concept. So in this case of velocity, our total effect, if we do this idea, would be our displacement, like how far we went, right? But think about what we're looking at graphically. Graphically, we're getting a value from our graph of a certain rate of change, right? So maybe 60 miles per hour, whatever. But we're also looking at an interval of time. And think about what we did when it was a constant velocity, like in the example I just gave. We said 60 miles per hour, the time interval was 2 hours. So if you have a certain rate, which is what we would get from our function, and we have a certain time interval, the way that we find out how far we went is by taking that rate, 60 miles per hour, and multiplying it by that time interval, which in my example was 2 miles per hour. Well, the problem here again is this rate, the length of this arrow is constantly changing. So we're going to have to deal with that in calculus. But the concept is going to be the same. Look what we're doing. We're going to take a rate and we're going to multiply by a time. And look at a time interval and look what that's going to give you. It's not going to give you a slope. It's going to give you an area. So physically here, when we are doing this opposite action, when we are trying to find out not how quickly something's changing, but the cumulative effect that it had over some time interval, what we end up looking at is an area, specifically an area under the curve. So the first thing we need to talk about in this chapter is how do I find that area under the curve? Because these are not areas you have formulas for. right? In geometry, they give you that beautiful formula sheet. And we know things like the area of a rectangle or a triangle or a parallelogram or a trapezoid or a circle. And we even learn how to take shapes that are made up of a rectangle with like a semicircle sitting on the top and find its area. But in this chapter, we're going to start seeing some areas that there's no formula for. But what's pretty cool is we can use calculus to find the area of any shape blob. It's going to be fun. All right, so like I said, whole new day in calculus, a whole new day. I'm sure that your life is filled with hope and possibility. Your calculus will be filled with rectangles and integrals for the next few weeks. And then forever, for the rest of your life, there will be rectangles and integrals because you'll never stop doing calculus. Ever. Okay, so our ultimate goal in this unit is going to be to find the area under any curve. We'll talk a lot more about what we mean by under a curve soon. But for now, I just want to talk about the general way in which we find the area under a curve. So there's a couple ways to achieve this. The first way that we achieve this is by approximating. I'm going to teach you two methods of approximating, one today, one tomorrow. The one we're going to look at today is called a Riemann sum. There are 3 different Riemann sums. It is less complicated than its name makes it sound. There's another method called trapezoidal approximation. I probably don't have to tell you what that involves. Trapezoid. Okay. And then we're going to learn how to find an actual exact answer. So we're going to have a goofy area in the curve. Using these methods I'm going to show you today and tomorrow, we'll be able to get a pretty darn good approximation. But if you want an exact answer, we're either going to use an integration method, which it's one little tick mark on my list. It's a lot of days. Or we can cheat with the calculator, thanks to technology. I call it cheating with the calculator, but in the end, unlike derivatives, where at some point I was able to say to you, okay, it's official, no matter what I throw at you, you should be able to take the derivative of this. That's never going to happen with integrals. So it's not that integrals can't be done for every function, it's just that we're not going to learn. So we're going to learn a certain number of methods. AP knows what integrals we should be allowed to do, be able to do, and which ones we shouldn't, but they do throw integrals at us that we can't do. They do it for 2 reasons. One, because they know that you have your calculator in your hand and you can cheat it using your calculator. And 2, they want to know that you know what you can and can't do. They give you something that you can't do and you start making stuff up. They know a little something about what you know, don't they? So we're going to start with the approximation methods. They're real quick. They're actually really easy. And then we'll go into the more kind of advanced integration methods and talk about getting some exact answers. All right. So again, we're going to start there. This is the easy part. All right. So when we are approximating in math, we always want to make sure that we have a method to approximate that is going to get us consistent answers, and we want to be able to get the same answer as somebody else. In other words, if I'm approximating and you're approximating, we want to be able to say, okay, this is the method we used, and therefore this is the approximation we got. We want to be able to have some idea as to whether or not our approximation is over or under. We want to have some idea as to how accurate our approximation is. So if you think back to when we did Newton's method, there was an algorithm that we went through so that even though we were approximating, if we all went through 5 iterations of Newton's method from the same starting point, we all got the same approximation, and we could tell ballpark how close we were. We could say, okay, we know we're accurate to at least 3 decimal places or to at least 4 decimal places, right? So we want to have something like that as well when we're approximating areas. So again, that method here is called a Riemann sum, or we call it RAM for short, which is rectangular approximation method. All right, so what we are going to do, rectangular approximation method, is we are going to use rectangles to fill up the area we're interested in. Now, our area is a curved area. So if we're trying to use rectangles to fill it up, it's not going to be perfect, right? So for example here, if I have this curve, I could say, you know what? I'm going to approximate this curve with one rectangle. I don't really feel like doing a lot of work today. And I draw this red rectangle in here, right? If I do that, my rectangle is 10 by 7, or no, I'm sorry, there's a 1 down here. So this is a 10 by 6 rectangle, which gives it an area of 60. Okay, now, I'm looking at this and I'm thinking, is it terribly accurate? Probably not. I can tell too that it's an overestimate because the area of my rectangle contains a lot of white space. But also notice that up here we left out a little bit of space. So my rectangle, if I wanted this whole shaded area, this rectangle isn't doing the worst job ever, but it's leaving out this little semi-triangular space up here. But it's including all of this white space that I didn't want it to include. So again, little left out and extra, but you can clearly see that there's more extra than there is left out. So is 60 a decent approximation? But I definitely know it's an over approximation. Okay, so one of the ways that we get our approximation better is that we make more rectangles. The more rectangles you make, the better your approximation will be. I want to show you some pictures of that. Okay, so originally my estimate, my terrible estimate, with one rectangle was 60 square units, whatever they are. Here I said, you know what, I'm going to divide this. I'm going to use 2 rectangles to approximate my area. So look what happened here when I used 2 rectangles. I went from 0 to 5 and then from 5 to 10 and made 2 rectangles. No reason they have to be the same width. That's just me being who I am as a person. All right, so I made my first rectangle be 5 by 2, which gives me an area of 10. So my rectangle has an area of 10. Again, look, there's a little triangle left out here and a little more included here. But these don't look that far off from one another. Right? So they're kind of balancing each other out. Then I made one that goes from 5 to 10, and it is 7 tall, so this is 35. And again, we have the same situation. There's a little extra that I left out here, but there's some here that I included that I shouldn't have, and these two are kind of going to balance each other out. When I use 2 rectangles, I get that I have an area of 45. Now, I knew this was high. We knew this was high. This looks like it's definitely going to be closer, and I've got 45. Now, more rectangles is more better, so let's do even more rectangles. Here I did 5 rectangles. So my interval is from 0 to 10, so I said, well, let me make 5 rectangles that are 2 wide. Again, no particular reason I decided to make them all consistent. I could make one that's 1 wide and another one that's 3 wide. There's no reason they all have to be the same. I like them to be all the same. Okay. When I did this, notice I made a rectangle that's 1 by 1, or I'm sorry, look at me, 2 by 1. 2 times 1 is 2. I'll just go ahead and fix that. This is 2. Act like you didn't see that. I know how to multiply. I swear I do. Okay. This one is 2 by 2, so it's 4. This one is 2 by 4, so it's 8. This one is 2 by 6, and this one is 2 by 9. So when we add those up, we get 44. Now, 2 things I want you to notice. Again, we have this same rectangle-y piece left out, extra piece situation here, right? So I have this piece that I should have included, but I included this triangle instead. They're about even. Same thing here. This was left out, but this was included. This little chunk here was left out, but this was included. This piece was left out, but this was included. This piece was left out, and there's a teeny tiny piece over here that was included that shouldn't have been. Okay? But this you can see visually looks a little more accurate than this. And here's what I want you to notice. My first approximation was 60. When I used 2 rectangles, it went to 45. Now that I used 5 rectangles, it went to 44. Does anybody smell a limit? I do. Notice this. As my number of rectangles is approaching big, the area that I'm getting is approaching some value. That value that it's approaching is the value. It's the exact area. This is just like when we took for slope those 2 points And we said, okay, that's the slope of a secant line. And then we pushed them closer and closer and closer together. And we looked at the slope of that secant line and went, hey, it's approaching 3. Well, bingo, bango, the slope at that point at the tangent line is 3. That's what's going to happen here. When you make the number of rectangles that you have larger, your approximation gets better. So theoretically, as the number of rectangles you have approaches infinity, your actual area, the area you're getting, is going to approach the real actual area. Now, I cannot physically draw an infinite number of rectangles. I can, however, use calculus to do it. And that's what we call an integral. When I draw an infinite number of rectangles and then somehow manage to add up an infinite number of rectangles. That's what an integral is, and we'll get there. But first we're going to approximate. Right? I drew one more approximation, but I didn't do the numbers because they were a little too hard to estimate. But as you can see here, I did 10 rectangles, and you can see that extra pieces are real small and the left out pieces are real small, and you're going to get an even better approximation here. The more rectangles you use, the better your approximation will be. Okay? But again, we're going to use this general idea, but we still need a way to know how accurate we are. If we have an overestimate or an underestimate, we want to make sure that we're consistent. We want to make sure that if I approximate using 5 rectangles and you approximate using 5 rectangles, that we both get the same approximation. Because we're math people. We need to know if we're right or wrong. It's really important to us. Okay, so I want to go through with you the 3 rectangular approximation methods. They're all RAM, rectangular approximations, Riemann sums. And then we put a letter in front to indicate where we get the height of our rectangles from. So the first one we're going to talk about is RRAM. We call it the right Riemann sum. Okay. So in that last slide, when I was putting in my rectangles, I was just randomly deciding. I was eyeballing how high I wanted my rectangles to be. No, we're not going to have that. Okay. We're going to decide how high, how are we going to choose how high to make our rectangles? That's going to be important to us. So if we choose to use RAM or RRAM, our right Riemann sum, what we are saying is that when we look at the interval we're interested in, so on this picture I have from 0 to 5, I broke it at the whole numbers because that's easy, right? So I broke it into 5 intervals, I'm sorry. If I have chosen to use right Riemann sum, what I'm going to do is I'm going to use the right endpoint of each interval, and that's where I'm going to get the height of my rectangle from. So the first thing I'm going to do is I'm going to look at each interval, and I'm going to put a dot at the right endpoint of that interval. Okay, so notice here on the interval from 0 to 1, 1 is the value I'm going to use, the y value at 1. On the interval from 1 to 2, I'm going to line it up at 2. From 2 to 3, I'm going to line it up at 3. So notice on each of these intervals, so from 4 to 5, I'm lining up on the right, on the right, on the right, on the right, on the right. Now it's hard to see when you're looking at these ones because there's a point on both ends, but it becomes evident when you look at the rectangle, when you're going to look at the rectangle on the end, because notice there's no end point over here, there's no value here, as I don't care about it. I'm lining up on the right. So if I use RRAM, if I use the right Riemann sum, my rectangles are going to line up on the right like this. So notice this first rectangle goes from 0 to 1, and its height is determined by this right endpoint. My next rectangle goes from 1 to 2. Its height is determined by this endpoint, the one on the right. My third rectangle, again, its height is determined by the right endpoint, by the right endpoint, by the right endpoint. So I'm going to find the area of each one of these individual rectangles, which shouldn't be too bad considering they have a width of 1, all of them, right? All I have to do to get their heights is all I have to do to get their areas is find their heights, really, and add them up. You can see from this picture, this is going to be an over approximation. Notice here, of all of the area under the curve, these rectangles didn't leave any area out. but they did include a lot extra. So if I do this, if I add these up, I know for a fact I'm going to have an over approximation. Okay, so that's a right Riemann sum. Okay. Well, obviously if there's a right Riemann sum, there's a left Riemann sum. So for a left Riemann sum, we're going to do the same exact thing. We're going to partition it into intervals, right? Again, if I'm going from 0 to 5, I'm going to just partition from 0 to 5. You'll see problems where they tell you how many intervals to use. They'll tell you how wide they want your intervals to be. It's just another way of telling you how many to use. Okay. So the first thing we do is partition. And again, if I want to do a RAM at the left this time, instead of lining up on the right-hand side for my rectangles, I'm going to line up on the left. So when I bring my dots in on the interval from 0 to 1, the value I'm interested in is the y value on the left. On 1 to 2, I'm interested in the value on 1. Right, so my rectangles this time are all going to be lined up at the left side of each interval. Notice here, it's the exact opposite of what happened with right Riemann sum. Here, I've got all this space left out and no extra. So I know for a fact this is going to be an underestimate. Okay. Now, I'm going to have you practice with this tomorrow because and today, one of the hardest things to do with RRAM and LRAM is to draw the stinking rectangles. I cannot tell you, and I still do it myself. I'll be drawing them, and then all of a sudden, I'm like, I'm lining up on the left, I'm lining up on the left, I'm lining up on the left, and out of nowhere, I start lining up on the right. It is actually sometimes a little bit difficult to draw them correctly. So it's one of the things that we just have to get practiced at. Once you're practiced at it, you'll be fine. But it's a little more challenging than you might think to draw the rectangles correctly and consistently line up on the same side, especially when you have a curve that's going up and down. So we want to get a little bit of practice with that. Okay, so far I have two options. I told you there's 3 RAMs. I can line up on the right, I can line up on the left. The third option is to line up in the middle. This always reminds me of the 3 Little Bears. Like this one's too hot, this one's too cold. In the middle. All right, so if I'm lining up in the middle, again, let's go back to my 5 intervals here. Instead of my points that I'm going to use being on the left or the right, they're going to be in the middle of each interval. So here they come. This one is at 0.5, this is at 1.5, 2.5, 3.5, 4.5. I like this one. So when I put my rectangles in, now, the height isn't going to come from the left and it's not going to come from the right. It's going to come from the midpoint of the interval. So I'm going to go up to the curve in the middle, and that's what's going to determine the height of my rectangle. Now look what happens when I do an MRAM to this function. What happens is what happened on the previous slide when I was just kind of willy-nilly doing it. Notice that for each section, there's some that's left out, right? This area, I should have included this, but it's not included. In an ideal world, these little yellow triangles would be included, right? But there's also some space that I included that I shouldn't have, right? In MRAM, it kind of balances out a little bit. So a lot of times, MRAM is a nice compromise for us. Okay. Now the thing is, the different approximation methods can be more accurate depending on the function. So we're either going to, when we choose which method, it's going to be either because they told us which method to use, which is so nice, just tell us what to do, or they give us a function and they tell us, hey, make sure you have an overestimate or make sure you have an underestimate. And that's when we can determine if our LRAM or our RRAM is going to be what's best for us. All right, and let's talk about why. Okay, if you have a function that is strictly increasing or decreasing, then you will be able to determine which RAM is going to be too big, which RAM is going to be too small. And then you'll know that MRAM is going to be in the middle, right? It's going to be what? Baby bear, right? So for example, up here, look, this is a decreasing function. Okay? So if you line up on the left of a decreasing function. Notice this, on every interval, your left is the higher endpoint. So if you're lining up on the left, if you're doing an LRAM, you are only ever creating extra area and you're never having any area left out. So if you have a function that's decreasing and you constantly line up at the left, then you're always making a rectangle that is taller than the function itself over that interval, because you're always using the absolute highest point on the interval because the function is always decreasing. So we know we're going to get an overestimate. The exact opposite happens if you do an RRAM, again, on a decreasing function. Where's my pen? Okay. So notice here, again, on my interval from 0 to 1, this function is decreasing. If I choose to line up on the right on this interval, I am choosing the absolute lowest point on this interval. Therefore, I know for a fact my rectangle is going to be too short. And I'm going to be leaving out space. Look, I left out all this space. So if you have a decreasing function, lining up on the right is going to cause it to be too low. And notice MRAM, it's a happy little compromise. Okay. Now the exact opposite is going to happen if you have an increasing function. If you have a function that's increasing, like we just had in our last example, then if you always line up on the left, you're always going to have an underestimate because you're always going to be using the lower point on the interval. But if you line up on the right, you'll always be using the higher point, so you'll have an over. M will be a compromise. But that's only going to work if we have a function that's either always increasing or always decreasing. If it's consistently increasing, then we know which side to line up on if we want to be overestimating or underestimating. If it's consistently decreasing, we know which side to line up on, right? If we want an overestimate, line up on the high side. If you want a low estimate, line up on the low side. But most functions aren't, right? Most functions increase and decrease and have intervals. So look at this picture. And this is what I'm talking about when I say it can get confusing how you're drawing your rectangles. So in this function, I've got this little wave, right? This function that increases for a while, decreases for a while, increases, decreases. Okay, so look, I've chosen to do a left endpoint here. So I'm lining up on the left. That's where I'm getting the heights of my rectangles. Notice that on the interval where it's increasing, my left endpoint is the low one. So this rectangle is too small. On this whole interval, though, where my function is decreasing, look what happens when I line up on the left. When I line up on the left, I chose the highest point on the interval, so those rectangles are overestimating. As soon as it starts to increase again, if I stick to the left, all my rectangles are going to be too short because I'm at the low point on the interval. And then over here, when it starts to decrease again, I'm using the highest point on the interval. But sometimes this can look a little bit funny to us. It doesn't look like the rectangles have been drawn consistently, but they have. Every single one of these rectangles, its height is determined by the left endpoint of the interval. Every one of them. It's because the function is switching from increasing to decreasing that we see some of them being over and some of them being under. Okay. Now contrast that with the right endpoint approximation, the RRAM. Again, they look very similar. You still have some that are too big and some that are too small, but it's been a switcheroo now, right? So on this first interval, instead of lining up on the left, on the low point, like we did over here, we're now lining up on the right. And on this particular interval, the right is the high point. So I'm going to get an over. When the function starts decreasing, my right endpoints are always the low sides. When the function increases, my right endpoint again becomes the high side. And then when the function decreases, my right endpoint is a low point again. Okay. Now here, what's better, LRAM or RRAM? I don't know. They both left some out. They both have some extra. I bet if we used MRAM, it would be best. Let's look at MRAM. Okay, there's MRAM. Let me move my face for you. Okay, so check out MRAM. Notice here, this first rectangle, see these dotted lines they put in the middle? That's the middle. And notice that the height of my rectangle doesn't come from the left or the right. It comes from the middle. Here, there's the height of my rectangle came from the middle of that interval. So again, it's like this little marriage of LRAM and RRAM. If we were in class, somebody would put their hand up right now and say, if I just average LRAM and RRAM, will I get MRAM? No, you will not. Sorry. M is not the average of L and R. It is a bizarre marriage of them, but it's not an average of them. We'll talk about what happens if you average them another time. But this is definitely not the average of these two. So, sorry. It's not what we want it to be. All right. Let me move my face again. Down in the corner where you belong, Britton. Okay. So, let's actually use this. We're going to do this same problem 3 times. We're going to use an LRAM, we're going to use an RRAM, we're going to use an MRAM. And we should be able to predict over and under here. Right? So if you look at this function, I have an increasing function. It's increasing the whole time. It's just t squared. So in this particular problem, I want to use an RRAM. So I want to line up on the right-hand side. Now, I don't know about any of you. I am absolutely, confession, I'm absolutely atrocious with left and right. I don't know what my problem is. I'm a 43-year-old woman, and I still do this and see which one is the L. I don't know. My dad always says, make a left, and then I turn right. He goes, other left. Ha ha ha. Okay, I can do integrals. I just left and right somehow escape me. Okay, so truly, maybe it's just me. I have trouble keeping track of the left and right on these things. So please be careful if you catch yourself messing them up. Just like, I'm going to use this method every time because I have trouble. If you're not having trouble and you can keep it all in your head, good for you. But if you're noticing that you're starting to switch where you're lining up, maybe just follow this process. So again, I draw my lines where I want my intervals to be. I'm on the interval from 0 to 3, so I partitioned at 1, at 2, and at 3. And then I'm just going to come in and actually draw my dots where I want them to be. Now for me, if I'm doing an RRAM, I literally start over here and draw back and down, back and down, back and down. Because if I don't, I somehow inadvertently switch to LRAM. Okay, so if I'm doing an RRAM, I literally start from the right-hand side and work my way back as far as drawing rectangles. Okay, so I would do, and I'm going to animate pretty ones here in a minute, but I would go like this. There and down, there and down. Okay, so I'd get 3 rectangles. That's how I do it. So let me animate in what it should look like, and hopefully you can draw them very nicely on your page. Okay, so again, notice I started on the right and I made that right. The rectangle goes from 2 to 3 has to get its height from the right hand side, from the 3. So if I'm drawing this by hand, I would start here, come back, and when I get to 2, drop it down. Okay. When I come from 1 to 2, instead of starting at 1 and trying to approximate over, I would just start at this dot, bring it over, and then drop it down. And then start at this dot, bring it over, and drop it down. Okay, now I do not have to guess at these heights. Again, I drew them by hand. They're not going to be perfect because I have a function, right? So these widths are all going to be 1 because of the way I partitioned it. All right, this first one lines up on the right. So this first one, the width is going to be 1. The height of this particular rectangle is just going to be f of 1. So in other words, 1 squared. So that first rectangle is going to have an area of 1. Okay. For my second rectangle, it still has a width of 1, but its height came from this point right here, which is f of 2, or 2 squared. So that rectangle has a height of 4. Now again, for a problem like this, you might just be looking at it going, duh, Britton, it's 4. But you're not always good. It's not always going to be right on a line. And you might need your function to find that value, and that's fine. Use it. All right, this last one, my third rectangle, again, it has a width of 1. Something you always want to verify. Don't just assume they're 1. Sometimes we see them where the widths of the intervals are 2. Sometimes we see them where they change, like one's 1, and then sometimes they'll all be 1, and just one of them is 2. Jerks. Okay. This one, its height comes from the right-hand side, or the 3, so its height is 3 squared, or 9. So I've got 3 rectangles. If I want to know what my area approximation is, I'm going to add that up, and I get 14. Okay, now, look at this. This was an increasing function. I consistently lined up on the right, which means on every single interval, I chose the absolute highest point I could possibly choose to draw my rectangle. So I know that this 14 is an overestimate. I know it is. I had an increasing function, and I lined up on the right, which is always going to be your highest point as long as the function is increasing. Because as you move from left to right, the y value is going up. So if we're lining up on the right, we're always grabbing the highest value. So even without a picture, that's got to be an overestimate. But visually, we can see it's an overestimate. Okay, I don't have to tell you what we're going to do next. We're going to do the whole stinking thing again, but we're going to do it from the left. Okay, so again, I want to come in here, and I want to draw my partitions. Whoop. I'm going to go from 0 to 1, 1 to 2, and 2 to 3. Except this time, I want to line up on the left. So on my interval from 0 to 1, I'll be at 0. On my interval from 1 to 2, I'll be at 1. On my interval from 2 to 3, I'll be at 2. So here come my dots. I'm lining up on left, left, and left. These rectangles for me are easier to draw, I think, because I'm drawing from left to right. Okay, so if I'm drawing these, I'm going to come across and down, and you will notice that my first rectangle doesn't even have a height. If I start here and go across, I'm at 0. So my first rectangle, even though it has a width of 1, it has a height of 0 because my height that I chose was 0. 0 squared is still 0. So my first rectangle isn't a rectangle. It's a non-rectangle. Okay. My next rectangle goes from 1 to 2, and its height comes from the left endpoint, so it comes from 1. So it has a width of 1 and a height of 1 squared, so it's a 1. My third rectangle goes from 2 to 3, so again, it has a width of 1, and its height comes from its left endpoint, which is 2. So 2 squared, or 4. And I add those up, and I get an approximation of 5. Clearly, that is an underestimate. Clearly. All right. And again, we can see from the picture it's an underestimate, but here's what we know, because they're going to ask us about this like in theory, right? This is an increasing function. We lined up on the left. So on any interval, as you go from left to right, if your function is increasing, then that left point is always going to be the absolute lowest point on the interval. It's got to be, which means every single one of your rectangles is going to be too short, and you're going to have underestimate. So here's what we know at this point. I don't actually know what this area is, but I know it's somewhere between 5 and 14. I'll bet MRAM can give us a better answer. MRAM to the rescue. All right, MRAM, I'm so glad you're here. Okay, so MRAM gives us a better answer, but I will say this. MRAM can be a little bit of a pain in the butt because you have to find the middles of all the intervals. And in this case, it's not that bad, but sometimes it can be a pain in the butt. It usually involves fractions, which everybody loves, but you know, it's whatever. Okay, so again, I'm going to start with my same 3 partitions, 0 to 1, 1 to 2, 2 to 3. And instead of going to the left or to the right, I want M this time, so I'm going to go to the middles of all my intervals. So now when I draw my rectangles, my first one isn't going to be lined up at 0. It isn't going to be lined up at 1. It's going to get its height from 1.5. Right? So my first rectangle in this case, it has a width of 1 like it did before, but now its height is f of 1.5. So 1.5. Oh my gosh, Britton. I know what the middle of 0 and 1 is. It's almost as good as 1 times 2 from before. I don't know what's better. 0.5. Sorry, my bad. Okay, so let's see. 0.5 is 1/2, right? 1/2 squared is 1/4. So my first rectangle has a area of 1/4. All right, my second rectangle still has a width of 1, but since it's an MRAM, I'm lined up in the middle. This point right here is 1.5, also known as 3/2. I'm keeping it as fractions because the fractions are easy to square. So I have 3/2 now, which is 1.5, and I'm going to square that, which means this rectangle has an area of 9/4. My third rectangle that goes from 2 to 3, so again, it's a width of 1, gets its height from the middle between 2 and 3, 2.5, also known as 5/2. And when we square that, we get 25/4. So now let's see. I've got 9, 10, 35/4. So that is just shy of 9, right? So if you take 35 and divide it by 4, who likes long division? It's going to go in 8 times, right? Get a 3, you bring it on down, 4 into 33. I'm sorry. 4 into 30 is like 7, 28, you get 2, you bring it on down, 8.75. Nobody did long division but me. I'm the only one. Okay, so MRAM says 8.75. Now, here's what I don't know. Is that an underestimate? Is it an overestimate? I'm not sure. Right? It left some out. It's got some extra, but visually I can't see where that balance lies. So I don't know if it's an under or an over. I do know though that it's probably my best approximation, right? We had before that it was somewhere between 5 and 14. 5 was clearly way low, 14 was clearly way high, 8.75 is probably going to be our best bet. Okay. Okay. So here's what I would like you to do other than ignore that because we're not there yet. All right. So hopefully today you were able to get through this and it made a little bit of sense to you. Tomorrow we're going to go over the other approximation method, which is the trapezoidal approximation method, and then there will be an assignment on the 4 approximation methods. So 3 that are rectangular, and then tomorrow's buddy that is trapezoidal. I think trapezoidal is a great one, and not just because the word trapezoidal is great, because it does a great approximation. I apologize for this ridiculously long video. It probably took you 6 hours to watch by the time you were done taking breaks listening to my mouth. I will see you virtually tomorrow. Have a great day.